With the ease of handheld capture devices, any public event can now be captured by multiple people from various perspectives. Our goal is to synthesize a novel view from a perspective that wasn't physically captured. That is, we are given multi-view images or videos with known camera poses and approximate temporal sync. We synthesize a novel view for a target pose and time. In this work, we introduce neural pixel composition for 3D 4D view synthesis from multi-views. Different from existing methods, our approach allows us to synthesize novel views from multi-view sequences captured from sparse and unconstrained cameras. Here, the minimum distance between the cameras is more than 50 cm. Our approach can synthesize novel views, whereas prior methods such as NERF and DS-NERF struggles. It also allows us to get dense depth map and 3D point clouds from sparse and unconstrained multi-views, can reconstruct small details. Here we show 12 megapixel novel views synthesized using our method for 3 multi-view sequences. We can see the small details in the synthesized view as shown in the bottom row. Prior methods are restricted to resolution lower than 1 megapixel. The proposed method also allows us to do detailed 4D view synthesis. Here we show better facial details synthesized using our approach in comparison to Open4D. Finally, the model can be trained quickly in 2 to 3 minutes as shown by the convergence plot for 3 different datasets. Yes, it has become easier to do multi-view captures, but it also brings important challenges. The minimum distance between two cameras in our setup is more than 50 to 60 cm, which is the minimum distance between two humans standing next to each other. This is different from existing datasets such as LLFF and shiny objects that have a very small baseline up to 5 cm. To illustrate this, we show a multi-view capture of an event with 10 cameras. Because the distance between two cameras is arbitrary, there's a non-trivial overlap between adjacent frames as shown here. There's a drastic illumination difference between two cameras even when they are close. The sparse and unconstrained multi-views also leads to noisy camera pose estimates. Finally, the performers in the multi-view sequences can be wearing challenging dress, have open hair, and the captured scene can be unbounded. Current approaches such as NERF yields degenerate outputs even when trained for 7 hours. Similarly, DS-NERF that used an additional depth supervision using sparse point cloud from ColdMap also degenerates. We move away from radiance field-based methods and use simple insights from multi-view stereo. Estimating disparity between a stereo pair allows us to project pixels in 3D space. A n-view multi-view sequence provides n-choose-2 stereo pairs. We build a dense 3D volume using n-choose-2 stereo pairs that contain multiple things at each 3D location. For example, there can be a red object in the background, green in the middle, and a blue object in the front. Our goal is to synthesize new view using this dense 3D volume. A simple solution is to use Z-buffer, that is, take color values corresponding to the closest points along the ray of light. This simple method does not require parametric model, however it contains patchy artifacts. One way to improve the simple method is to average the color values corresponding to the 3 closest points. This yields slightly better results, but it still contains artifacts. In this work, we use a simple multilayer perceptron that predicts alpha values for compositing. MLP can be trained quickly in 2 minutes and require 1 GB GPU memory for training. The simple method allows us to get detailed outputs. We show novel views synthesized using our method for multi-views captured at 4 different timestamps. We also contrast the results of our approach with NERF and DS-NERF for other challenging multi-view sequences. While other methods struggle, we are able to synthesize realistic novel views for these challenging multi-view sequences. Not only this, our approach also allows us to synthesize 12 megapixel high resolution details quickly in 10 minutes. This allows us to see small details in the scene. NERF struggles to capture these details even when trained for 32 hours. We trained NERF for 64 hours but did not see any further improvement. We also contrast our results with next that requires multi GPU to train a model for multiple days. We can also use dense 3D volume for dense 3D reconstruction from sparse and unconstrained multi-views. We visualize the dense 3D point clouds from two multi-view sequences using MeshLab. For more analysis, please see our paper or come talk to us at the Tuesday morning poster session. Thank you.